Welcome to Chem 201. Today we're going to go over Introduction to the Course, the ion test, and Chapter 10, Lewis Structures. The first thing we're going to talk about is the websites you're going to need for this course. So let's head over to SDSU Blackboard. Alright, so what you want to do is you want to click on the Chem 201 Spring 2016 Extended General Chemistry course. Right now it's currently unavailable because I'm still working on it. Alright, on here you'll be able to click on the syllabus right here, as well as go to the Chem 201 website. So let's first go over the syllabus. So we're going to click on that. Now let's take a look at the Chem 201 Spring 2016 syllabus. As you can see, I have written out the website right here, but it's also linked in your Blackboard. The text you'll be using is the Silberberg Chemistry 7th edition Chem 201 manual as well, with the lab notebook. You need to make sure you have the Chem 201 lab manual from Tina and George. You will need to purchase the lab notebook, and this book was given to you last semester in Chem 200. Again, you need to have your lab apron, safety glasses, and non-graphing scientific calculator. The grading for this class consists of the Chem 201 grades. So to pass this class, you need to have at least a 65%. The points will be distributed as such. 3 midterm exams, multiple choice, they're 100 points each. The final, multiple choice but comprehensive, will be 200 points. Your quizzes will be best out of 8 out of 9, 20 points each. 4 worksheets that will be given in your recitations, which are on Wednesday. You'll need to do an ion naming test. It's required to pass the course, so if you do not take this exam or pass it by your first exam, you will not be able to continue on with this course. There are going to be 7 lab reports, 2 group unknowns, and a general unknown, giving a total of 1,000 points. Quizzes will be given in the recitation sections on Wednesdays. They'll be based on lecture material from the previous week. A homework assignment will be given in lecture, but not collected. It is to help you prepare for each quiz. So you can do it, you cannot do it, it's up to you. The midterm exams will consist of 20 multiple choice questions, and they'll be given on Tuesdays at the regular scheduled lecture time. The final exam will consist of 40 multiple choice questions, based primarily on questions from the 3rd midterm exams. There will be a few questions based on material covered in lecture after the 3rd midterm exam. Here's our schedule for our spring lecture. As you can see, the first 2 weeks will be online, so there'll be lecture videos. This week we'll be going over the first part of Chapter 18, a little bit of Chapter 10, Chapter 3, which you've seen in Chem 200. Chapter 17 and the first part of Chapter 18, you definitely saw in Chem 100. So this is just going to be pretty much a review. Then we're going to get into Chapter 18, weak molecular bases and weak ionic acids and bases, which is more Chem 201 style. Then we'll get into Chapter 19, which will not be on your first exam. Your first exam will be Chapters 3, 10, and 18. Technically, it adds with Chapter 17, but it's a very small section, as you'll see. Your Exam 1 will be on May 3rd, after your holiday, so make sure you study. We will definitely have a review, which will be done by Yorgi. So he will announce to you what time he will have the review for you. I'll be in town on May 2nd, so on Monday. So you can definitely email me, or we can schedule some time to work out problems if you like. It's up to you. Just send me an email at tcarlson@mail.sdsu.edu, and I'll be happy to help you out. And then here we have the rest of the schedule. So Exam 2 will be on May 17th, Exam 3 on May 31st. June 6th to June 10th will be just a review for the final. And then finals week is starting after June 10th. Your labs will be on Monday and Friday. The first day of lab will be introduction and review of your ION test. During your recitation, that will be the first time you will have your ION test. If you pass this exam, you get an extra 5 points. Yay for extra credit. And then on Friday will be your first experiment. So make sure you come well prepared and you have your pre-labs done. Experiment 2 will be on Monday, which will be your experiment 1 report will be due as well. Then you have your ION test second try, as well as quiz 1 and 2. As you can see, there's a lot of work ahead. During finals week, though, you will not have any labs. All right, going back to the Blackboard, I want you to click on the Chem 201 website. So this is the website I put on the syllabus, and here is the link in your Blackboard account. So click on it. So it'll take you to the Chem 201 Spring 2016 webpage. Unfortunately, the only thing that's going to pertain to you will be the downloads. So click on that. So on the download section, you'll be able to see the homework and homework solutions for this semester, some lecture overheads, practice exams and study guides, quiz solutions for this semester. Again, not for you guys. This will be like an old exam for you. Exam solutions for this semester, again, will not be for you, so use it as an older exam. Quizzes from previous semesters and exams from previous semesters. And as you can see, there's a lot of exam practice you can get with solutions, how to do calculations, etc. So this is really going to help you out through the course. We also have it for the quizzes as well. So use this as a good study tool as well as the homework I assign, because this is a great way for you to ace this class. Now, this is the ion naming tests, common ions. You can find this on your SDSU Blackboard. It'll be under course documents. So here, this is what you're going to be seeing: your normal cations, your anions, your polyatomics, which you remember from your Chem 200. So you just want to make sure you know these. You also need to remember how to name your ions. So for example, you have aluminum chloride. What does that mean? Well, the formula is AlCl3, because aluminum is a cation with a 3+ charge, and chloride is an anion with a -1 charge. Don't forget, your transition metals will need to have Roman numerals to them. And it has a practice exam attached to it. So try it out and see if you get your answers correct. This will be a best way to know if you're going to pass the ION exam and to receive the 5 points extra credit if you pass the first round. So just to review, let's go over the structure of matter. So we have our fundamental particles: electrons, protons, and neutrons. Electrons have a -1, protons are known as +1, and our neutrons are 0, neutral. The protons and the neutrons reside in the nucleus, and the electrons are in an electron cloud. In S, P, D, and F orbitals, there are 2 electrons per orbital. Orbitals are arranged in shells, so we have the first shell, which is our S orbital, has 2 electrons. Our second shell, which has the S orbital, the px, the py, the pz, remember the p orbital has 3 suborbitals to it, giving us 8 electrons. And our third shell, the s, px, py, pz, dz2, dx2 minus y2, dxy, dxz, dyz, gives us 18 electrons. Remember, the d orbital has 5 suborbitals to them. From our fundamental particles, we get atoms. So if we lose or gain valence electrons, we get ions. They can either be a cation with a positive charge, an anion with a negative charge, or we get covalent bonds with shared valence electrons, which will give us molecules or metals. If our molecules or metals lose or gain valence electrons, they become ions. Remember our goal: get more stable electron configuration, fill the valence electron shell. With our ions, we get ionic bonds because we have a positive and a minus charge. We can get our macroscopic material formed by our ionic bonds as solids, liquids, and gases. Now for molecules and metals, they use intermolecular interactions: ion dipole, dipole-dipole, and dispersion forces. We learned this in Chapter 12 in Chem 200. In our macroscopic material, solids are strong with intermolecular interactions, while liquids are weak intermolecular interactions, and gases have no intermolecular interactions. So let's take a look at chemical bonding. Remember, there are three types: ionic bonding, covalent bonds, and metallic covalent bonds. Let's first look at ionic bonds. It's electrostatic interactions between a cation and an ion. So let's take a look at an example: lithium fluoride. Lithium is our cation, fluorine is our anion. When they bond together, they become completely ionic. Now let's take a look at covalent bonds. Covalent bonds are shared electron pairs between two atoms, nonmetals. So let's look at fluorine, difluoride. They're both anions, and when they bond, they form the covalent bond, and for this molecule, it's a non-polar covalent. This fluorine right here is more electronegative than hydrogen, so if we had hydrogen and fluorine, for example, we would get a polar covalent bond right there. Now with metallic covalent bonds, electrons share over many atoms. So let's look at lithium solid. As you can see, lithium solid is just like an electron pulling. That's what we call metallic bonding. Now the important difference between ionic and covalent bonds is ionic bonds are broken when solids dissolve and covalent bonds are not. This is very important to remember. Now let's go over the structure of molecules and polyatomic ions involving main group elements. So the octet rule predicts bonding, and our VSEPR predicts the shape. Remember, sometimes we do break the octet rule, so don't use that as your rule of thumb. What is the octet rule? The octet rule is the main group of elements form bonds so as to give each atom an octet, 4 pairs of valence electrons. Exceptions: hydrogen is on the first row of the periodic table, so it only needs 2 electrons. This means hydrogen can only form 1 covalent bond, so it will always be on the periphery, the end. So let's take a look at carbon, for example. Carbon needs 4 bonds and has 0 lone pairs. The possible bondings of carbon looks like this. It can have 4 single bonds, or 2 single bonds and 1 double bond, or 1 single bond and 1 triple bond, or 2 double bonds. Nitrogen, on the other hand, needs 3 bonds and 1 lone pair. So the possible bonding for nitrogen are 3 single bonds and a lone pair, 1 single bond, 1 double bond, 1 lone pair, or 1 triple bond and 1 lone pair. Now nitrogen can have a positive charge. Why? Well, nitrogen is normally electric positive, so it prefers to be a cation. So if nitrogen is positive, that means we have an extra electron to its center. So let's look at this. So that means it has 4 possible bonds to it. and 0 lone pairs. Now let's take a look at its possible bonding. Just like carbon, it's going to have either 4 single bonds, or 2 single bonds and 1 double bond, or 1 single bond, 1 triple bond, or 2 triple bonds. Please make sure you remember to add that positive charge. Now let's take a look at oxygen. Oxygen needs 2 bonds and has 2 lone pairs. Its possible bondings are 2 lone pairs and 2 single bonds, or 2 lone pairs and 1 double bond. Now, because oxygen likes to be electronegative, because it's further to the right of the periodic table, if we made this oxygen negative, it's going to have 1 possible bond and 3 lone pairs. Now let's take a look at its possible bonding. It's going to have 3 lone pairs and only 1 single bond. Fluorine, which is our halide, is going to have 1 possible bond and 3 lone pairs. Now let's take a look at its possible bonding. It's going to have 3 lone pairs and only 1 single bond. Now, if you remember in Chapter 10 in Chem 200, we went over VSEPR, valence shell electron pair repulsion. VSEPR, in order to minimize the repulsion between like charges, groups of electrons, they orientate to get as far apart as possible. That's why we see 3D structures. The group of electrons means electrons in bonds or lone pairs. In VSEPR, all bonds, single, double, or triple, just count as 1 electron. So let's take a look at the VSEPR geometries. For a VSEPR geometry of linear, it needs to have 2 electron groups. So that can be a lone pair, a single bond, or 2 single bonds, or a triple bond and a single bond, as long as it's 2 next to the X, which is our central atom. Linear geometry is always going to have a 180-degree angle. Now let's take a look at 3 electron groups. This will be our trigonal planar, which will have an ideal angle of 120. Now notice the 3 bonds are in plane. They're solid sticks. Trigonal planar means everything is in plane. Now once we get into the 4 electron group, that's when we start seeing things going out of plane. We get the solid wedge and the broken wedge. So our first one will be the tetrahedral. The tetrahedral has an angle of 109.5 all around. Now let's look at trigonal bipyramidal. Trigonal bipyramidal is going to have 3 solid lines. It's going to have 1 solid wedge and 1 broken wedge. Between the solid and the broken wedge, you're going to have an angle of 120. Between the lines, solid lines, it's going to be an angle of 90 degrees. Now, our equatorial sites is going to be this solid line right here and the broken wedge and the solid wedge, while our axial sites will be the top and bottom lines. Trigonal bipyramidal is the only geometry with non-equivalent sites. Lone pairs prefer the equatorial sites. That is very important because if you remember, trigonal bipyramidal has other names to it when you add lone pairs. Now for the octahedral, which has 6 electron groups to it, it's going to have an angle of 90 degrees all around, but when you go from the solid line to this solid line, it's going to give you an angle of 180, so don't forget that. Let's go over the guidelines for writing Lewis structures for main group inorganics. Now let's place the atoms relatively to each other. If not, given any other info, assume symmetry. Hydrogen has to be periphery, meaning at the end, and oxygen usually is as well. Not all the time, but it is usually. Peroxide, for example, H2O2, the oxygens are in the middle. Now let's determine the total number of valence electrons available. Don't forget to consider any charges. Draw a single bond for each surrounding atom to the central atom and subtract 2 electrons per bond to give the number of valence electrons remaining. Then you're going to distribute the remaining electrons in pairs so that each atom has an octet except for hydrogen. You're going to start with terminal atoms on the periphery. If still have valence electrons left, after satisfying the octet rule, put them on the central atom. This gives the central atom an expanded octet. That means it goes beyond the 8 electrons. This is okay if the central atom is on the 3rd row or greater of the periodic table. So for example, nitrogen, oxygen, and fluorine can never be an expanded octet. If the central atom doesn't have an octet, move a lone pair from a terminal atom to form a pi bond. Repeat until octet rule is satisfied. Alright, so let's talk about some resonance structures. The first one we're going to talk about is the equivalence resonance structure. It has the same distribution of formal charges. An example of this would be O3, which is ozone. So we would normally just draw this with only the single bonds, and then we would add in our electrons. Now we know with ozone that it's going to have a negative charge and a positive charge to it, which gives us a net neutral charge. Now, ozone can also be written as this, where the double bond switches. So instead of being on the right, it's now on the left side. So it's an equivalence resonance structure. That means same distribution of formal charges. Now let's look at another example. Let's take a look at carbonate, CO3, 2 minus. Now carbonate, we know the carbon goes in the middle. We draw in our 3 oxygens as such. And because we have a 2 minus charge, we know that 2 of these oxygens are going to be negative, and 1 of these oxygens is going to be neutral. So this gives us CO3 2 minus. Now carbonate has 3 resonance structures of equivalence. You can move the double bond to the right or to the left. So let's draw out the other resonance structures. So here you go. Carbonate has 3 resonance structures. Now the second type is non-equivalent resonance structure, which means it has different formal charge distribution among resonance structures. So let's take a look at an example of bromide trioxide. Now we know that bromine has 7 electrons around it and oxygen has 6. Well, one of these oxygens will be negative, but let's try drawing different ways of this. Now one way we can draw this is all the oxygens have a negative charge, and the bromine has a 2+ charge due to only having 1, 2, 3, 4, 5 electrons around it instead of the 7. Now the next figure, let's add a double bond. So let's add it onto this electron, this oxygen. Sorry about that, small oxygen. So now bromine has a +1 charge, and we have 2 oxygens with a negative charge. Now let's add one more double bond. So now we have one oxygen with a negative charge, and bromine has 2 double bonds, 1 single bond, and a lone pair. So as you can see, the charges are completely different for each different resonance structure. So this will be called non-equivalent resonance structure. Now let's take a look at what a different compound is. So for example, we have C2H6O. Now we can have our carbons as central and our oxygen on the side. Let's just add in our hydrogens. So we drew this structure, and this is known as ethanol. And because of its hydrogen bonding, it's going to have a boiling point of 78.5 Celsius. Now we can draw this another way, where we can take the oxygen and make it into the middle. So let's draw this one out. This compound is known as methyl ether. And because all it has a dipole-dipole moment, it's going to have a lower boiling point. So remember in chapter 12 we talked about intermolecular forces and how it affects boiling point? Well, here the boiling point is -24 Celsius. So it's a lot lower than it is for ethanol, because ethanol has hydrogen bonding, while methyl ether only has dipole-dipole. So let's see if you can get this structure and name it. So we have C3H7O2. Now if we draw this out, we have carbon, let's put a nitrogen at the end, carbon, maybe a carbon here, an oxygen, and an oxygen. And then we add our hydrogens, hydrogen, hydrogen, one pair. This one needs a hydrogen to it. This one needs 3. I'm just going to slim it down. And a hydrogen here. And that gives us 7 hydrogens. So if we look, these aren't happy because they give us a negative charge when we add in the electrons. So for every 2 hydrogens short, we're going to start adding a pi bond. So let's do that. So let's redraw this structure and let's add in a pi bond. And we're going to start with the left with the nitrogen. So here is one structure. As you can see, I added the double bond right here. Now let's move this double bond over to here and see what we get. As you can see, moving the double bond, we have a new structure. So let's do this again. This time, we're going to move the double bond to this group. Now here is our new structure.